Yeah, I think we can start. Maybe we can wait for a couple of more minutes. Meanwhile, why don't the attendees introduce themselves? So I see a couple of new faces. So did any one of you join last week's session? By the way, am I audible? Anyone, am I audible?
Yes, audible.
Yeah, fine. Thank you. So I think while people join, we can start with, right?
Okay,
So
okay, okay, okay. Okay.
yeah. So welcome everyone. This is NOC 25W110 tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudeb Dasgupta from IIT Roorkee. I am Debashish Nandi from IIT Kanpur. So as you know that this will be for 12 weeks and today we are at the second week. Maybe followed by after 12 weeks there will be a summary session of whatever we have covered. So it is a 2-hour session and we go live every Saturday from 7 to 9.
Okay, okay.
So yeah, there is a couple of prerequisites. So I do reiterate these things for first 2 weeks. So that I assume that you all have tried at least the week 1's assignment that is due by 6th of August. And yeah, and also that you have gone through the lecture series, whatever is there for week 2, and I think now week 3 has also been posted yesterday. So please watch those lecture series before attending this session. It will be very helpful. And I think that you also have got the recorded lecture sessions of these tutorial sessions as well over some Google Sheet. Okay. So a couple of decorums, please keep your microphones muted unless I request you to unmute. And also there will be some doubt play. If you have any doubt, you can obviously unmute and interrupt me. And also there will be, I think more than 10 minutes we should have at the end of the second hour so that you can ask your queries, right? So the plan for today this is week 2, 2nd August. So yeah, so somebody raised the hand. Upendra.
Sir, excuse me, sir.
Yeah, sure, please go ahead.
Sir, regarding week 1, can we get it updated, sir? That means your lecture.
Whatever the tutorial session I had organized last week,
Hello, sir.
the lecture session I had organized last week.
No, no, sir. Regarding this microelectronics. Yeah, yes, sir.
Okay, so that is there in this session, this link. Okay, so you will get it from NPTEL team. Okay.
Okay, sir.
Please keep yourself muted.
Sir, it is not visible, sir. In NPTEL, it is. We can observe now, sir.
Yeah, sure. So I'll share these things over, or you can just go to my YouTube channel. So there will be this playlist available. Okay.
Okay. Your YouTube channel name is Debashish Nandi.
Yeah. So there you will get this W110 playlist where I upload the lectures, these tutorial sessions every week.
Okay. Thank you, sir.
Yeah. Please keep yourself muted. Thank you. So the plan for today will be mostly to cover the BJT working, okay, and the circuit aspect of the BJT. We will cover a couple of little issues we can cover this week, but most of them will be covered in a comprehensive manner next week, but via some examples. Okay, so let's begin then. So the question is that if we were to compare energy diagrams of three pieces of semiconducting materials, two are doped as N type and the middle one is doped as P type. So how do you draw the band diagram? So how many of you are comfortable with the band diagram and how many of you cannot at all uh, draw the band diagram or do not understand? Maybe you can respond in the chat. So are you all comfortable with the band diagram? I am talking about energy band diagrams.
Yes, sir, band diagram. You say anything about band diagram will be good for me. And same thing that
There is
that
some electrical noise coming out from your microphone.
the screen.
Yeah, please go ahead.
Hello,
Yeah, please go ahead.
hello, sir.
Yeah, please go ahead.
Am I audible?
You are audible. Please
Yes.
go ahead. Okay. Anyway, maybe some technical issue. So anyway, I'll just handhold you for this part. So I understand that many in as most of you are from undergraduate background, so there is a uh, correct way to draw the band diagrams, right? So I'll be just going over that. So a couple of things that what we are going to discuss is how to correctly draw the energy band diagrams. Okay, so a couple of pointers that energy band diagram is a two-dimensional plot. Okay, it is a 2D plot.
Voice is very low, sir.
My
Your
voice is
voice is
very low.
coming very low.
So can anyone else confirm if that is the issue with?
Your voice is fine, sir.
Okay, I think that is the issue with your end. Uh,
Okay.
okay, so you can anyway, if you cannot follow properly, you can watch the recording session as well, right? But maybe you can just unplug your headphones and then try to listen it over the actual device. Maybe it may help. So band diagram is a 2D plot. So as for any 2D plots, we need to identify what is the x-axis and what is the y-axis first, right? So what is the x-axis in the band diagram? Anyone? It is position along the material for which we are going to draw the band diagram for, right? And what is the y-axis? Y-axis is your electronic energy. So there is a difference between your energy and electronic energy. So electronic energy is basically minus q times potential. Phi is your potential. So now can you tell me, if I increase any voltage of any particular contact or to a particular material, where should the energy band be go, upwards or downwards? The y-axis of the energy band diagrams are electronic energy and electronic energy is minus Q times potential. So can you, any one of you tell me, if I increase the voltage, the conventional voltage, as we know, I am going upwards at the electronic band diagram, energy band diagram, or downwards?
Downwards.
Downwards, right? So let us keep that fact in mind. So as my energy or electronic energy increases, my potential decreases, okay, or my voltage decreases. So you should keep this in mind. So another important point is, what are the energy bands? First of all, what is energy band? What is an energy band? So you may be wrong, please answer, it will help.
A collection of energy levels, different energy
So
levels.
why does it happen in semiconductors? You know, for hydrogen atoms you have discrete energy bands, right? Discrete energy levels starting with minus 13.6 electron volts towards, and it moves as minus 13.6 by n square ev, right? As you, n is your principal quantum number, right? Now for silicon, if I talk about silicon, how many electrons does silicon have? What is the atomic number of silicon? Atomic number is 14, right? 1s2, 2s2, 2p6, then 3s2, 3p2, right? Is that okay? So now what is the, how many number of electrons do we have in our valence band? We have 4. That is the third orbital, right? So now if I take, consider a single silicon atom, I will have these discrete energy levels. Let's say this is your 1s, this is your 2s, very closely there will be 2p, then there you will have 3p, 3s, and there you will have 3p, right? Okay, so these discrete energy levels are true for a single atom, but when you move into a semiconductor material or a slab of semiconductor, there will be more than one atom for obvious reasons, right? Then what happens? Let's say these are two silicon atoms, okay, and these two are apart by a distance, let's call x. So if x is infinity, then we have discrete energy levels. Fine. Now what happens when we start to reduce x? If x is reduced, then you see this entire thing so what I am doing, earlier it is very far, okay, now I am trying to bring this closer to the other atom. So what is happening? Does the line will the lines superimpose exactly on top of the energy, or there will be some gap? Can you comment, anyone?
there will be gap.
There will be a little gap, right? And why that is so? Because your Pauli's exclusion principle states that in a system no two electrons should have the same quantum number, right? That means, and no two electrons should have exactly the same energy. So they will try to cope up with the same energy, but there will be a little gap. Now imagine how many atoms are there in 1 centimeter cube of silicon. Last time I have told you, right? It is 5 times 10 raised to 22 per centimeter cube. So now imagine that many number of electrons times you have 2 electrons, right? 2 times that many number of 3p electrons you will have at closely dense at it nearby each energy level. So you will have something like this. So many number of energies, but very loosely, very tightly packed and creating this kind of bands. Okay, so that is why this is called your energy bands. Okay, there are other fancy diagrams as well. If you can plot, for example, this is one way to represent. Another way to represent is that if you, the x is the interatomic distance, right? Now if you try to bring x smaller, then let's say this is your 3p energy level, then what happens, your 3p energy level will start to split, and then at between these energies there will be, this is your 3p band. Okay, and it is so that the interatomic distance of silicon falls at this region, so that you will have this kind of bands. Similarly, other bands will also start to split. Okay, and between two bands there is something called forbidden energy gap. That means no electron can take place, can take those energy levels. Okay, so now in case of band diagram, what do we draw? What is my x-axis then? I draw my band diagram at one point. For example, if I draw my band diagram, it will be like this. This is my EC conduction band, this will be my valence band for silicon, right? Now assume, so basically what is happening? So what is this x? This x is the distance between two silicon atoms. Okay, be mindful of that. And what is this? Let's say this is your z direction. What is this z? Z is the position along the silicon, or position along any material for that for that concern. So now if I draw my these 2 points with position, so I go to my energy band diagram. Okay, if that is fine, then next point is, what are the important energy levels in the band diagram? What are the important energy levels in a band diagram? So you know about EC, you know about EV. What is EC, what is EV? You know about EI, you know about EF, and there is something called E0. So once you understand what I am teaching you right now, so you will be able to draw energy band diagrams for any material, believe me. This is the very fundamental stuff, okay? So please tell me, what are these things? What is EC?
Conduction band energy level.
No, it is not conduction band energy level. You should be more specific.
The uppermost, bottommost part of the conduction band.
Exactly. This is the bottom edge of the conduction band, okay? So why we are concerned about the bottommost point? So let's say I have, this is my conduction band, okay? So why am I concerned about only this edge? Can anyone tell me why this is EC and this part we generally do not concern about? Anyone? The reason being that electron, or for that matter any object in this world or in this universe, try to attain the lowest energy level, okay? Even if, let's say, you have an electron at this point, it gains some energy, it will lose and fall back to this conduction band edge via a mechanism called scattering, okay? And by those scattering, it will lose, the energy is lost by in terms of heat, or it is transferred in terms of heat, okay, or your lattice vibrations. So that is why we are concerned about the conduction band edge only, okay? So this is your conduction band edge. And what is EV? Similarly, this is your valence band edge. What is EI? EI is called the intrinsic Fermi level. EF is your Fermi level and E0 is your local vacuum energy level, okay? Now let's say I have three material as asked in the question. Let's say I have these three material. So this is your N-type silicon, this is your P-type silicon, and this is your again N-type silicon, okay? And they are not jointed. What does they are not jointed mean? If they are not put together, that means these are individual system. So this is your system 1, this is your system 2, and this is your system 3. Fine. Now let us try to draw the band diagram for each of these. So I am drawing this line as E0. So remember one thing, when the materials are not jointed, means when you start drawing the band diagram, your vacuum level or local vacuum energy level should be constant, okay? Because that has nothing to do with the materials. It is in vacuum, just above the material, okay? So now next what we will draw? Let us draw EC. Then we will draw EV. So this is your EC, this is your EV, and let us draw EI. Now tell me, where should I draw my Fermi level for n-type material? Is this okay?
No, sir. Closer to conduction band.
So it should be closer to conduction band, right? So let's say this is my EF. Similarly for p-type, this is my EF. Similarly for n-type, this is my EF. Okay. So what is EF? What is the definition of EF? What is the definition of Fermi energy level? One definition you can give, for example, if you consider your Fermi-Dirac distribution function, you have this type of form, right? You have this type of form. So EF is that energy for a non-zero temperature where your probability of finding an electron becomes 0.5. Okay, that is one definition, but that does not convey any message to you in case of your band diagram, right? So alternate definition is, it is the average energy of electrons in a system, right? Please remember this definition. So now where should my Fermi level go? If I dope it with more n type, if I increase the doping concentration, it should go up or it should go down?
Up.
That means what is happening? The number of electrons, if it is an n type, the majority carriers are electrons. So if your number of electrons are increasing in the systems, obviously your average energy of the electron will increase. Fine. So that means your EF will move upwards or EF will increase. So that is why EF is the average energy of electrons in the system. Fine. Similarly, if you if you increase the doping in your p type, the concentration of holes will increase, and by virtue of your Np equal to Ni square or N0 P0 equal to Ni square, your hole concentration, your electron concentration will come down. That is why your EF comes down and goes closer to the valence band. Okay, so remember that Fermi level is the average energy of electrons in a system. So now tell me, what are these? What is this distance? What is this called? And what is this? Please unmute and tell me, what are these things that I am drawing? What is Eg?
Energy band gap between.
So Eg is your silicon energy band gap. What is the value at room temperature? It is 1.12 electron volt. Okay. By the way, what is Q chi? Anyone? What is this energy?
Work function.
No. This is called your electron affinity. And the value is 4.05 electron volt for silicon. Okay. So first tell me that this material is silicon, this material is silicon, and this material is silicon. Are you okay with that much? And then we are doing some kind of doping, either by phosphorus to make it N type and by boron to make it P type. Fine. But the base material is your silicon. The way you are telling that in each case, either be it N type or P type, your energy band gap will always remain same. What is the energy band gap for an N type semiconductor and what is for P type semiconductor? If the semiconductor is silicon, so it will remain 1.12. Okay, under normal conditions, if you don't dope it, like for example, your silicon atomic density is 10 to the power 22 per centimeter cube and you are doping it with 10 to the power 21. That is not the case. Then it will start to form alloy. For normal doping scenario, around 10 to the power 14 to 10 to the power 18, 19, your band gap will remain same. Fine. So this is something called a material property. Okay, this is a material property. That means it is same irrespective of the doping. Similarly, your electron affinity, the energy required for an electron to escape the material completely, that is called your, from conduction band to vacuum level, that is called your electron affinity. I am sure that in your 11th or 12th you must have read these things. At least the terminologies you must have been aware of. So electron affinity is also a material property. Fine. It does not matter whether you dope it with any type of semiconductor and whether you bias it or not, whether you apply voltage to it, these two things will never change. Fine. This is one important point to remember while drawing the band diagrams. Next, we define this energy. What is this? What is this energy? This is called Q phi S. Anyone? So without knowing these things, if you are drawing the band diagrams, that means you are doing something wrong. Okay. So Q phi S is the work function. That is the energy difference between the vacuum level and your Fermi level. Okay. So now tell me, is this a material property or will it change with doping?
Yes, it can change with doping
So
because my
this is exactly, so this is what we call induced property. Okay. So these three vertical dimensions of energy you should be aware of. One is electron affinity, that is a material property. Another one is your band gap, that is a material property. That material property means the base material on which you are doing the doping, the base semiconductor. But the work function depends on doping. So that is an induced property. Okay. So now in the question it is asked that equilibrium band diagram. We need to draw the equilibrium band diagram. So what is equilibrium? Can we have a discussion on equilibrium? Any one of you want to volunteer?
Having the same work function.
having same work function? No. We will see, we will come to that is not the case. So if I tell you what is equilibrium, the question remains incomplete. Okay, so this concept comes from thermodynamics. Okay, and what does thermodynamics talk about? What kind of energy thermodynamics talk about? Thermal energy, right?
Thermal energy, yes, sir.
So equilibrium is actually your thermal equilibrium. Okay, so whenever we talk about equilibrium in case of semiconductor devices, we talk about thermal equilibrium. Okay, and there are certain conditions the system needs to understand these things. The system needs to maintain or be at thermal equilibrium. First condition is constant temperature. If your system is not at equilibrium, you cannot define temperature. Okay, that is for one thing. That comes from directly from the laws of thermodynamics. So for thermal equilibrium, one thing is constant temperature should be there and no other sources of energy. That means thermal energy is the only energy that is allowed when anything is, we call it is in equilibrium. For example, let me ask you one question. If you can see a semiconductor, can you comment on its equilibrium state? Is it in equilibrium or not? If you can see an a semiconductor block, is it in thermal equilibrium? Can anyone comment? You can say yes or no. Only two options are there, right? Yes, if it is, then that is also fine. If it is no, then that is also fine. We'll have a discussion and we'll learn something new. So anyone, if you can see a semiconductor, is it in equilibrium? I need an answer before I proceed.
Yes, sir.
Is it is in equilibrium if you can see a semiconductor?
No, sir. At room temperature,
At constant room temperature or at
yes.
constant temperature, if you can see an semiconductor, is it in equilibrium? What do you think? Should it be or should it not?
Mm,
No, sir.
I think no, sir.
Why?
Because,
Just
sir,
if you think yes, then you can answer yes. That is fine. Yeah, please go on.
because, sir, I saw in one video that when we heat the semiconductor, then it is go into the conduction mode.
So what?
So,
If electrons go from valence band to conduction band, that doesn't mean that it is not in equilibrium. I am putting it at a constant temperature, right? By definition, it should be in equilibrium. But will it be if you can see it? The catch is in you are able to see the semiconductor. That means what? There is presence of light. That means there is presence of light energy, another form of energy, right?
yes.
That means if you can see an semiconductor, it is not in equilibrium, because the first condition of thermal equilibrium states that only source of energy that can be present is constant temperature. That constant temperature can be 0 Kelvin, can be room temperature, can be 700 Kelvin, anything, but stipulation is constant temperature and no other source of energy. If you are able to see it, there has to be light, so there has to be presence of another form of energy. So this is a very trick question generally asked in most of your interviews what you are going to face, that if you can see a semiconductor, please remember that it is not in equilibrium. Okay, I think I have made my point. Second point is no net transfer of energy across any cross section. So for something to flow, you need a cutout, right? Or you need a cross section. So if, let's say, well, if I say that there is no net motion of energy or net transfer of energy, what does that mean? Does that mean that there is no transfer of energy at all or no movement at all? That is not right. This simply means that if something is moving from left to right, the equal amount should be flowing from right to left, so that the average, the net energy transfer is 0. Okay. Third point is no net flow of carriers. Okay, by means of diffusion or osmosis, nothing, there should be no net motion of carriers. That means if something is flowing from left to right, equal amount has to be flowing from right to left, the same thing. And another very important point which most of the textbooks do not refer to is the principle of detailed balance. What does that mean? Principle of detailed balance says that the cross section we are talking about, right? If that area of that cross section, if you tend it to 0, that means however small system, subsystem from that system you can take, the equilibrium conditions should be valid. Fine. That means for even for a large, let's assume a hose pipe and water is flowing out and some water is coming in, so that the thing is in equilibrium. Now if I keep reducing the area of that hose pipe, then also the laws of equilibrium should be valid. So this is called principle of detailed balance. Okay. Now tell me one thing, if EF or the Fermi energy level in a system tells you that it conveys you the idea about average energy of electrons in a system, what it should be in equilibrium with respect to position in that system. So the question is, let's take any system. Okay, so I want to draw the Fermi energy level. Can I draw it like this? EF at equilibrium, what will happen if the energy is like this? So there is, this point is at higher energy, higher average energy. EF is what? Average electron energy in the system. So this point is at lower energy, right? If you have some energy gradient, then there will be flow of carriers. But that is not possible. If I take my cut section or the cross section at this point, I will always see a flow of energy in this direction, right? So that is not allowed. So how should my EF look in case of equilibrium? Anyone? Guys, please try to interact.
A straight line.
A straight line can be this also, right?
A straight line with no slope, basically.
That means a constant line.
Constant line, yes.
So at equilibrium, your EF has to be constant by the definition of equilibrium, okay? So D of EF with respect to D of X, so let's say this is your X direction, should be equal to 0 for a system. Fine. If we are good till this far, so let us proceed with the band diagram of the entire system. So earlier what we had, we had these three blocks. This is n-type silicon, p-type silicon, n-type silicon, right? And what was the bands? This was my E0, then somewhere here I had my EC, somewhere here at my EV, this is EC, this is EV, and this was my Fermi levels, right? So the catch is that this was system 1, system 2, and this is my system 3. Now what is asked, that I need to make them a single system. Fine. So this was my EFs. So now I need to make them a single system. Let's say this is my N, this is my P, this is my N. So by end the system is in equilibrium. So what is the first thing that should happen in this case? What is the first line I should draw? The first line I should draw a constant EF, because now this entire thing is my system. This entire thing has become one single system, and the system is in equilibrium, and in that system across any cross section there cannot be a gradient of energy or the average energy of any carriers, right? That means my Fermi level has to be constant. Is that okay with everyone?
Yes, sir.
Now what we will do to draw the band diagrams? First thing we will try to see, so what will happen? So let me divide some regions. So okay, let me just, so let's say I am dividing this into these regions. So this is my region 1, this is my region 2, and this is my region 3. What I have done, at the junctions I have removed, I have kept some places for reserve, and apart from that what I will see, that from in region 1, region 2 and region 3, my n-type, p-type and n-type will behave exactly like n-type, p-type and n-type. So I should be able to draw the energy band diagrams very easily seeing these things, right? So where should my, so this should be my EC, this should be my EV. Similarly in this case, this should be my EV and this should be my EC. Similarly here, fine. So this is my EC, this is my EV. Because away from the junction, my p-type, n-type and n-type, p-type and n-type will preserve its own nature. Fine. And what am I seeing? That this band gap has to be same irrespective of whatever system I put, because my base material, entire base material is silicon. Okay, please do not forget that. That is my material. So everywhere I should have the same band gap Eg. Similarly, what should I have? I should have my Q chi or electron affinity also same. That means I can simply draw my Q chi like this. Why? Because this is my Q chi. This has to be same throughout the material. This has to be Q chi. Similarly, this has to be 4.05 electron volt or Q chi, right? So now what will I do? I'll just join the bands. Now let me focus on first this region, okay? These two bands. By the way, one important point, that if Q chi and Eg are material property and the entire thing is entire material or the entire thing is silicon, can I say that my E0, this is E0, is parallel to EC is parallel to EV? Can I say this? Whatever the line may be, if my E0 is like this, EC will be like this, EV will be like this, right? Can I say that? Anyone? Come on, I need an answer. Can I say that these three lines will be parallel if we have the same material? Let's say my valence band is this, okay? So at each location, my conduction band should also be like this, because at each point the distance between these two is Eg. Similarly, between conduction band and E0, if the material is same, at each point it has to be Q chi. So this statement is true. Is it okay? Is it okay?
Yes, sir.
So now tell me if that is fine with you. So I need to track only E0. So I can just draw EC and EV parallel to that. Fine. So now at this green juncture or junction, I need to join these two black lines, okay? So this is these two black lines I need to join. So this is my E0, for this is my, let's say, N type, and this is P type, and this is also E0. So how should I join? Can I join like this? That means, can I join like this?
No, sir.
Why?
Because we are changing the distance between two silicons, and I think by adjusting the distance between two silicon atoms, as we take the example of first,
Okay.
uh, I think that is one solution.
So where do you see that your silicon atom distance are changing? Silicon is at the background. Silicon will have the same atomic distance, that is 5.43 angstrom or 5.43 times 10 raised to minus 10 meter between two atoms. That has absolutely nothing to do with this. That will be absolutely same always, because that is what is determining your band gap, right? So your Eg is constant, right, throughout the material. That means your distance between two silicon atoms that determined your band gap, this x will always be constant for a material. That this implies that your Eg is constant. This is your Eg, right?
Yes, sir.
So why cannot I join it like this? So okay, so what is this black line? Please tell me that much. What does this line signify? Which energy level?
Sir, it's local vacuum energy level.
It is local vacuum energy level, right? So have you come across this? So I have mentioned that electronic energy is equal to minus q times of the potential, right?
Yes,
Is
sir.
that okay? And what is electric field? Do you know this thing? Electric field is the derivative of this. Electric field is a negative
Yes.
differentiation or derivative of the potential. You are okay with that?
Yes, sir.
So what will be electric field in terms of energy, electronic energy? Can I write this? So basically this is nothing but in 3 dimension gradient of your energy. Is that okay?
Yes, sir.
Now tell me, what is this function look like? If you have done your signal system, how does this function look like?
Unit step.
Exactly. So this look like some kind of step function, right? So what is the derivative of step function?
Impulse.
Impulse, right? Or your Dirac delta function. What is the magnitude of impulse function?
Infinite.
That means at this point, what is your electric field?
Infinite.
Is that possible?
No.
So that means what? That tells me immediately that I cannot join two bands of a same material like this. So what I can do? I need to have a smoother transition, right? Now tell me, if I have a smoother transition of E0, can electric field be infinite anywhere? In this case, electric field cannot be infinite, right? Obviously I can see that if I draw the electric field, this is constant, so it will be 0, and then the slope is increasing, right? At this point the slope is maximum, and then again the slope is decreasing, so again the slope will decrease and this will constant, so this will be like this will be my electric field profile. So it is not infinite, right? So that means the way I will join my band diagram is like this. Is that okay?
Yes, sir.
But what is the catch? That at each point, this value is q time chi. Fine. At each point, this value is Eg. Because this is a material property, it will never change. For a same material, it will be always same. Fine.
Okay.
If that is okay with you, so this is how the Venn diagram of an NPN diode, NPN transistor at equilibrium looks like. So now will you be able to draw it for PN junction and other transistors, for example PNP? Please follow the steps and draw it with some logical reasoning that why it should be. Again, this is something called qualitative energy band diagram, not quantitative. For quantification, you need to tell me that what is the distance around which the band will bend. That can be easily found, but that is something advanced for you. Okay, so we call it qualitative energy band diagram. Okay. So now you can ask me any questions regarding this, whether you are comfortable or you want me to repeat any part. And there will be one small problems what you can try. If you have understood the concept what I have told you, you should be able to let us make it silicon and this n type is germanium. Okay, so silicon q chi is 4.05 electron volt, germanium q chi is 4 electron volt, Eg is 1.12 eV, Eg is 0.67 eV. So this you can try at home. So okay, one more thing I need to tell you, draw the equilibrium band diagram. Okay, fine. So if that is so, by the way, this thing is called, because this entire stuff is silicon across your NPN, these junctions are called homo junctions. Okay, because it is a junction between silicon and silicon, albeit it can be of any type of semiconductor, p type or n type, but the junction from the base material is homo junction. So there should not be any discontinuity at any of the bands. E0 cannot have discontinuity irrespective of homo junction, or this kind of junction is called your, where two types of materials are there, this is called hetero junction. Okay, no by the way, this thing is called discontinuity, this sudden jump is called discontinuity. That means limiting sense, you are approaching a same point, you are finishing at two different locations, right? This is a discontinuous function. So continuous function is what? By approaching at the same point from plus side and minus side, if you are reaching the same point, that is a continuous stuff. But when you are approaching at different points, because at 0 minus you are at -1, at 0 plus you are at +1, so this is something called discontinuity. Heterojunctions, no discontinuity in E0, but EC, EV can have discontinuity. Okay, remember these points and you try to solve this. So this will be the homework part. Okay, fine. This will further clarify your concept, and then in the next week's session, if you found any difficulty or if you did not understand any of the jumps you were observing, the same process you will start. You will start with two different things and a constant vacuum level. You will start with two different materials, silicon, germanium, p-type, n-type. You start with constant vacuum level because vacuum level does not have anything to do with the materials when they are disjointed. Then you draw these things, values I have already given you. Then when they both of them are combined, then the entire stuff makes a system. Then you come back and draw the constant energy level and again check what are the vertical dimensions and then draw the bands accordingly. And E0 you make it continuous because at vacuum there cannot be infinite electric field, right? From the definition of electric field, this here we have seen. So if that is fine with you, then you start drawing the EC and EV following the Q chi and EG convention, and then see that at the junctions where the EC and EV are ECs in silicon and germanium finishes, because in the region where the material is silicon, your Q chi will be same, but as soon as you go to your this germanium, your Q chi changes and your E0 will always follow the EC in that material. So you can see that there is a sudden jump or discontinuity at EC. That is completely fine, okay, because you are changing the materials. But E0 is irrespective of materials because it is at vacuum, so it cannot have any discontinuity. Okay, so try to draw this. And let us, I think this will cover the band diagram aspect of your PN junctions as well. If you want to understand the band diagrams in your textbooks, now once you have understood this part, you can just go and then check that everything is falling at place. So okay, so let us move on to the next question. So it is asked that bipolar junction transistor functions usually considered in terms of currents. Okay, this we have seen at in the last class. A relatively small current through one of the transistor's terminals exerts control over a much larger current. Draw the directions of all the currents of these two transistors, clearly identifying which is the control and which is the controlled. Okay, so can you voluntarily comment? So this is your, let's say, PNP. Okay, PNP transistor. This is your emitter, so this will be P plus plus, this is N plus, this is P minus. We will see what is this. So this is your WE or the emitter width, this is your base width, and this is your collector width. Okay, and the doping is, let's say this is Ne, this is Nb, this is Nc. So you can say, why did not I write Pe, P, because it is P type, but the general convention is to write the doping with N as a capital letter, and then you can change the subscripts. Okay, it is understood. So now can you tell me the relation of these things, the doping and this? what I mean to say, let us first consider about the width of the regions. So what do you think, which has the highest width and which has the lowest width in the BJT?
Collector has the highest and base has the lowest.
So that means your WB is less than WE is less than WC. That is what you have told, right?
Yes, sir.
Okay. So that is correct. So the key aspect is that your base width determines the transistor action. Okay, we will see how. And your collector width is increased because, why is collector width largest?
To tackle the power dissipation and to get more number of electrons.
Because of,
Power dissipation
yeah,
control.
that is one point, but important point is your collector base junction is reverse biased. Okay, so if your collector width is smaller, then most of the voltages will appear at the collector base junction and can damage that. Okay, and also you are absolutely right that your collector for improving the power handling capability, you can have your larger collector. Okay, what about the doping? Which one is the highest and which one is the lowest?
Emitter is heavily doped.
Emitter is heavily doped, and then your
Then the
base, then your collector. Is that okay? So if I draw the doping profile, let's say mod, and I take it in log scale. Okay, so it will be, and let's say these are the junctions. So let us make base a little narrower. So it will be something like this. So this will be around your 10 raised to 20, unit is centimeter cube. Per centimeter cube, that is the dopant number of dopants per centimeter cube of silicon. So this will be around your 10 raised to 18. This will be around your 10 raised to 16, and again this will be around your 10 raised to 20. So this entire thing is your collector. Okay, so a couple of pointers that we will see that why this is happening. I'm just mentioning it here that emitter is highly doped because to increase emitter injection efficiency, and what will happen to the collector, why this collector is lowly doped near the junction with respect to base,
to tackle the early effect.
exactly, to tackle the early effect or the base width modulation. Okay, we will see that as well. But can anyone tell me Why this the collector width is again increased? Collector doping is again increased after whenever we are away from the junction. Why it is again increased?
Because sir, our end goal is to achieve the same amount of electron in as we have injected in the emitter in the collector as well. So I guess for that
So
reason.
you are absolutely right, but can you tell it in some other way? So what will happen if your what will happen to resistivity if your doping is lower? So your rho collector is your 1 over sigma collector, right?
Yes.
And sigma,
So it will increase.
sorry,
Sir, it will increase.
resistance will increase, right? Resistance, for example, what is the collector resistance? Rho collector times L collector by area of collector. Okay, and what is rho collector? 1 over sigma collector times L collector by, now what is sigma? Your
NQ mu.
NQ mu, right? So what is this NQ, or to be more precise, what is this N? This N is nothing but your collector doping. So in one case you can see that your collector width is more, right? That means your length of the collector is more. So the resistance is in this way, right? So how can you mitigate that resistance? If there is some, let's say there is some current flowing and it is seeing some resistance, so there will be obviously potential drop. You will not be able to get the exact output what you are trying to get. Or in the other term, what that other fellow has just said, correctly pointed out, that you need all the electrons to get out of the collector, whatever emitter is injecting, right? So this resistance will block that. So that is why what you do, you dope it higher so that this term is reduced, because this is your higher, so that the overall resistance can be controlled. Okay, this is called to control your series resistance effect. You must have seen this term in case of high forward biased scenario in your PN junctions. Okay, so this is how the doping and dimensions of the BJT looks like. Now how the current flows into that. So let's say I am taking two scenario, PNP and this one, and then I will just change this to NPN. Okay, so what will happen? First thing, if it is at equilibrium, what will happen? There will be formation of depletion region. Is that okay? If nothing is connected, so there will be depletion region. Similarly, in case of NPN, there will be depletion region. And the depletion region in a PN junction is more at what side? Lowly doped side or highly doped side?
Lowly doped.
Lowly doped side. So we know that, so this is your emitter, base, collector, emitter, base, collector. So your emitter is highly doped, so your at your EBJ, the depletion region will be more at the base side. Similarly, between base to collector junction, it will be more at the collector side. Fine. So at equilibrium, you can see that from the band diagram. Where is this? This is the depletion region where the band bends. Okay. This is the depletion region where the band bends, and wherever the band is constant, there is no space charge. Okay. Or for example, there is no charge. You can directly derive it from Gauss law. So now this is in equilibrium. So what is the most common mode of operation? We do the forward biasing of the EBJ, right? So let us forward bias the EBJ. So this junction is forward bias. What will happen? First thing that will happen, holes will be injected. Similarly, electrons will be injected, and okay, let me just use different colors. Okay, so holes will be injected. In this case, electrons will be injected. In this case, holes will be injected in this way, and in this case your electrons will be injected this way. So what will happen in case of your forward bias? These holes will cross this barrier and your depletion region will plummet, right? And this holes will recombine here. Similarly, these electrons will also be injected towards your emitter from the base side, and again this will recombine. Okay, same thing will happen this way as well. So now tell me, how many of you do not understand recombination and why it will recombine? So this is your electron trajectory, this is your cold trajectory. So how many of you do not understand that why they will recombine? So what is happening basically? Here holes are majority, here holes are minority, electron majority, electron minority. Fine. Now when these holes have crossed, when it is at this location, no, when it is at this location, what will happen? My holes, whatever has traveled from emitter to the base side, has become a minority, and it is seeing a lot of opposite majority electrons. So by law of nature they will try to recombine. if they recombine, then as I go along in this direction, the hole concentration will drop. Excess hole concentration that have crossed the emitter base junction will drop, right? Is that okay? And it drops at exponentially proportional to a to the power x. This is if this is the x axis. Is that okay?
Yes, sir.
Now tell me, what happens if my collector base junction is far away from the emitter base junction? All of the holes are recombined in the base region. This region is lower, right? So now what I have to do? I have to bring this junction leftwards. That means I need to make my WB smaller, so that before this entire thing is recombining and getting vanished, my sum of the holes crosses the collector base junctions as well. Fine. And what will happen, and how should I bias my collector base junction? So this is P type, this is N type. So to attract holes, what voltage should I have here? Whatever holes are passing this way, to attract them, what should I have at this terminal? Positive voltage or negative voltage?
Negative.
So that is why this junction is reverse biased, so that your holes can get collected at the collector end. Okay. Now if I track the currents, so there is this current. So what is flowing at this junction? Only holes are flowing. Current will flow along the whole junction. So this is my IE or emitter current. Okay. Similarly, where at this junction or at the base terminal, only electrons are flowing. So current should flow opposite to the electron. That means current is flowing in this direction. That is your IB. Okay. Similarly, at this junction, holes are flowing. So this is my IC. Okay.
Yes, sir.
And a certain portion of the current, so direction of current is this. This is called your IBR, or your recombination current in the base region. Okay. And what is this current? This is IE. Current direction is opposite to the flow of electron. This is IEN. And this current at this point, one portion of the emitter current is going this way, another portion is this way. So this current is known as IEP. Okay. And this current is your ICN, which is almost equal to IC. What are the two currents that I have not shown? There is some current will be flowing in this direction. Okay. So in this direction, that is your ICO, or your reverse saturation current. And also there will be some recombination happening in the depletion region as well. Okay. So there will be this current as well. So we generally ignore these two current components that I have drawn in orange color. Okay. So now what I have at this junction, if I use KCL, I will have IE equal to IEP plus IEN, right? Similarly, at this junction, I will have IB equal to IBR plus IEN, right? And at this junction, I will have IC equal to, or your IEP equal to IC plus IBR. These three equations are okay. So now if I manipulate, my IE becomes, I put IEP equal to IC plus IBR plus IEN, right? What is IBR? IBR is nothing but IB minus IEN. So KCL is valid in the overall region, okay? IC plus IB. Now a couple of definitions. Your IEP divided by IE is known as gamma. This is called your emitter injection efficiency. So basically what does it tell? So when will it be, when will gamma be more? Can anyone comment? So your IE is IEP plus IEN, right? When this quantity will reduce, then this will try to reach IE and this gamma will try to reach 1, right? How can you reduce your IEN or this current, or in other words, this flow of electrons? How can you control this? How can you reduce this? This is basically reduced by making doping of emitter greater than doping of base, okay, so that the back injection or electrons towards the base is reduced. Fine. If more electrons come into the emitter region from the base region, then most of my holes that is injecting from the emitter will get recombined at this place. That we do not want, right? We want whatever we are injecting at the emitter should get collected at the collector. So this is called emitter injection efficiency. This is why the doping of emitter is kept higher than the base. Another term is that your IC by IEP is called beta. This is called base transport factor, B. This is called base transport factor. So why it is called base transport factor? Basically, whenever your holes are transporting.
Hello.
Yeah.
Hello.
Yes, please go on. Please go on. So whenever your holes are transporting through base, so how much current is dropped, that measure is given by this base transport factor. Basically it is this quantity that is getting dropped, right? So now if you multiply these two, what do you get? You get your IC by IE, that is your alpha. Okay, similarly your IC by IB is called beta, and obviously you can establish from IC plus IB equal to IE relation, you can find out that your alpha is equal to beta over beta plus 1. Okay, so these are the current gains in the transistor. You can similarly track the currents in NPN transistor. Okay, just follow the same nomenclature and make sure that you note the direction of current flow opposite to the electron and towards the direction of the flow of holes. Okay, so now the question is, what kind of configuration is this? Emitter is at lower side, so we can safely assume that this is a common emitter kind of configuration, right? So what will be my currents? For in case of PNP, current is flowing inward to the emitter. This is IE, going outward at the base. This is IB, and going outward at the collector. This is IC. Similarly, if you see, this will be just the opposite for NPN transistor. Now can you tell me which is the controlling current and which is the controlled current? In this discussion, what current I am trying to control?
IC.
So IC is controlled current. And what is the controlling current?
IB.
Why not IE? In this configuration, IE is the controlling current, right? Because this is a common base scenario. The base is common between this is your input port, this is your output port. The base is common here. So your controlling current is IE, not IB. Similarly, in this case, so this becomes your input port and this becomes your output port. So in this case, your IB is controlling. Okay, and similarly, if you see, this is your output, this is your input. So in this case, IB is controlling, but in case of common base kind of scenario, the one I have drawn the full-blown diagram, your emitter current is the controlling current. Okay, I think that answers the question. So how many of you have gone to electronic circuits lab, or at least have seen a digital multimeter, the yellow or orange stuff?
I have seen it, sir.
So did you notice something called diode check option?
Yes, sir.
Or why does it use, or why do we use it, the diode check option?
Sir, because we have to
Because you have to do what? It is used to identify the what is the P terminal and what is the N terminal of any kind of junction. Okay,
Yes, sir. Yes, sir.
that is the diode check option. So this question they have asked that if technician uses a multimeter's diode check function to identify the terminals on a BJT. So you are given a BJT, some cylindrical object or some flat object with some 3 terminals, and you need to identify which type of BJT it is. First question. So what type of BJT this is, PNP or NPN, and identify what is which terminal, which terminal. Okay. So for that you need to understand first how does this diode check option works. Okay. So basically you have a battery and then you have a current source, and then this is the place where you control the current junction, and this is the voltmeter. So by the way, what is the voltmeter what is the series resistance of a voltmeter? You studied in 11th, I guess. What is the series resistance of a voltmeter? Should it be infinity or should it be 0? What is the voltage, what is the series resistance ideal series for a ideal voltage source? Last class I have discussed.
Ideal voltage source should be very low.
0, right?
Zero.
Ideal means 0.
0. Yeah.
But in case of voltmeter, what is the ideal series resistance?
Infinite.
Exactly. So basically there you have a series resistance that is infinity. So it is just used to measure the voltage across any device. Fine. So if you are aware of the diode characteristics, let's say this is a diode, please note the directions. If this is your VD and this is your ID, and if I plot ID versus VD, so my diode characteristics look something like this. Are you familiar with this?
Yes, sir.
Okay, so now let me say that I am connecting this diode, okay, in this fashion. I do not know whether which side is P, which side is N, but just for the symbology I am using it in this way. So and I am injecting 1 milliampere of current. So this is, let's say, the 1 milliampere of current, and this is minus 1 milliampere of current. Okay. So what if it is a silicon diode? What will be this voltage? What is this voltage for a silicon diode? So this volt. So what is the diode relation? Diode relation is Is times exponential Vd by eta Vt minus 1, right? So after your 0.6 or 0.7 volt, you will have a huge rise in the current, exponential rise, right? That means you can approximate it is like that. Whatever up beyond this current level, how much you increase, your voltage does not increase much, because it is then the logarithm function of the current. Logarithm function is a very slow function. Okay. Anti-exponential is your logarithm. So this generally ranges at 0.5 to 0.7 volt. So if this reading shows 0.5 to 0.7 volt, I can safely say that the diode is connected in forward bias. Okay. Now, now what if, but diode is reverse biased? A very huge 1 milliampere is a huge current for a diode, for a solid state diode or PN junction silicon diode. So if I am injecting 1 milliampere and this, then it should show the Zener voltage or the knee voltage. If it is an avalanche diode, it should show the avalanche knee voltage, right? And this voltage is typically around your 1 volt for your 14N001 kind of diode. Okay. So then if it is 1 volt it is showing, or the magnitude it will show 1 volt, or ideally it is minus 1 volt. So you can safely say it is in reverse biased. Okay. So just by reading you can tell that whether the diode you have connected is in forward bias or in reverse bias. And obviously you know that this one is your positive probe, or this one, and this one is your negative probe. So you know that whether you have connected it in the positive terminal or in the negative terminal. Fine. Now in the given question it is mentioned that you have a transistor with 3 legs, 1, 2 and 3. When it is connected between 2 and 3, when it is connected, the positive one is connected to 2 and the negative one is connected to 3, it is showing a reading of 0.605. So it is forward biased. That much you are sure, because it is falling in the range of 0.5 to 0.7 volt. So that means this terminal is your P, this terminal is your N. That means 2 is P, 3 is N. So this much you have identified, right? Now what you are doing? You have connected to 1 and 3. Again 1 positive and 3 negative. And you are seeing that it is connected in forward bias. So again 3 is already N, you know, and now also it is validated. So 1 is your P type. Fine. So what is the type of the diode? Type of the transistor? Transistor type is PNP transistor. Okay. Now we need to find why, if it is a PNP transistor, then the N stands for base, right? So this 3 terminal is your base. Now we need to determine whether this P terminal or this P terminal, which one is emitter and which one is collector. How can you tell from these 2 readings which one should be what? Can anyone try to take a guess? One reading is a slightly higher than the other reading. So can you tell me which one is emitter and which one is, whether one is emitter or collector? Anyone? How about Molly? Can you try?
One is emitter.
One is emitter. Why do you say so?
So because IE is equal to IC plus IB.
So this is voltage reading, right? This is voltmeter reading. This is basically giving you this voltage in the diode characteristics. So you can say the reason is emitter is highly doped than your collector. Okay, your Ne is highly doped than your collector. So this voltage, will be very much nearby to your built-in voltage of the diode. And what is the built-in voltage of the diode? It is Vt times log of n emitter or collector times n base, because that is the n region, divided by Ni square. So if your Ne is greater than this, then your Vbi of Ebj will be greater than Vbi of Cbj, or the collector base junction. Is that okay? And because it is in the logarithm, so that is why the difference is not that much. What does a log function do? A log function compresses a wide range to a very small range. That is the reason why you use your log paper, okay, or log sheets or semi-log sheets. The reason, because when you try to plot something that is exponential or power law, square, cube, so after some point you cannot draw it in a sheet of paper. If you use log scale or log paper, you can compress that. So power function becomes linear, exponential becomes linear, right? So because of Ne is much greater than Nc, that is why the cut-in voltage of the emitter base junction diode is slightly more than the cut-in voltage of collector base junction diode. That is what is being shown. So by the value you can tell which terminal is emitter and which terminal is collector. Is that okay? Anyone? Anyway,
Sir, here you are suggesting that you are measuring the built-in voltage, right?
I am not measuring the built-in voltage. I am giving you the sense of the built-in voltage. Built-in voltage cannot be measured because built-in voltage is an equilibrium concept. Whenever you are in equilibrium, whenever you are connecting the metal contacts of the terminals, no, these metal contacts, the potential will get balanced and you will see nothing in your KVL. If you apply KVL, you will see nothing. Built-in voltage cannot be measured. I am telling you about the cut-in voltage. There is a difference between cut-in voltage and built-in voltage. But what I am suggesting, that by knowing the built-in voltage, you can have the idea about the cut-in voltage or the sense of the cut-in voltage, whether it should be higher or lower. Is that okay?
Yes, sir. But I have that query in my mind because in some fluke manual I have read that they are giving the options of measuring the built-in voltage. I think
Built-in
that
voltage cannot be measured. Built-in voltage is an equilibrium concept. Even if you try to measure it, you have to inject something. What I am injecting, I am injecting I test. So by default, I am not in equilibrium, right?
right, sir. And that also I want to ask that the current that you are injecting, it is in the it is inside the multimeter, right?
It is
The
inside the multimeter. Yes, that is being done by this 9-volt battery that you are adding at the back side, right?
okay, sir.
This is powering up that current source, and that current source, because this is infinite resistance, will flow through this. Because of the series combination, and you have an almost ideal current source, so 1 milliampere has to flow through this diode. Now the question is whether this diode is in forward bias or reverse bias. Does this make sense?
Yes, sir. Yes.
Okay. So yeah, so let us do one more question. So region of operation, I have told you, depending on the condition on EBJ and CBJ, you can have your region of operation and your application. Okay, so what are the biasing conditions? Let's say reverse biased, reverse biased. This is reverse biased, this is forward biased, this is forward biased, this is reverse biased, and then this is forward biased, this is forward biased. What is the region? Can anyone tell me? When both the junctions are reverse biased,
Cutoff.
it is cutoff. If the emitter base junction is reverse biased and collector base junction is forward biased,
reverse active.
This is reverse active. Then forward bias, reverse bias is your forward active. And your forward bias is saturation, right? So what are the applications, by the way? This cutoff and saturation are the switch operation. This is the off state, this is the on state. Okay, switch I have explained in detail in last class. What is the application for forward active? Amplifiers. What are the applications of reverse active? Anyone? Bad amplifier or chopper circuits. Okay, when you want to chop off some of the portion of the any waveform. So why it is a bad amplifier? For amplification we have seen, right, that my emitter, this thing has to be higher, this thing has to be lower, and this region has to be higher, drop has to, this length has to be higher. It is everything opposite direction, right? As if you are applying this biasing condition, this biasing conditions, just opposite. So as it is PNP, obviously it will have the same transistor action, but the amplification will be very bad. Even you may get some kind of attenuation as well. Okay, attenuation means amplifier with a gain less than 1, that is called attenuation. So for a, let's say, how do you draw the characteristics? So this will be, let's say, this, you have something like this. So let's say this is your IC common emitter I am considering, this is your VCE. Okay, so if it is a common emitter, I can simply put the reference potential at ground. Okay, I can put this ground and provide input here and take output at here. So this is my IC, right? So basically I am just changing VC, okay, because VCE is VC minus VE. It will be more easier for you to understand. Fine. So this is, so let me just compartmentalize the entire thing. So this is one region, this is your one region, this is another region, and this is another region. Okay, okay, so this is another region. So let's say this is my VBE2, VBE1, VBE1 let's say around 0.7 volt, VBE2, VBE3 which is greater, this is VBE4. Okay, so basically VBE is increasing this way, VCE is increasing this way. So now can you tell me what is the green region?
Saturation.
And what is the condition for saturation? Do we meet it? Saturation condition is both has to be in forward bias, right? So if I am above this dotted line, if I am above this line, so my VBE is greater than 0.7 volt. That means EBJ is forward biased. Fine. And what about CBJ? What about collector base junction or VCB? VCB is equal to VC minus VB. So VC is my N terminal, VB is my P terminal. So to make this forward biased, I need to have a lower value of Vc than Vb. My Vc has to be Vb, then only my Cbj will be forward biased. So that is why, as I am at lower Vb, lower Vc, right? So my this junction will get forward biased. As soon as my Vc crosses, this is the line where my Vc is greater than Vb in this direction. So that means in this case my Cbj is reverse biased, and already I am at above this line, so my Ebj is forward biased. So this is your forward active, this is your saturation, and at this location, where am I? Beyond, I am already beyond this line, so my Cbj is reversed bias, and beyond Vb less than 0.7 my Ebj is reversed biased. So this is my cutoff region, and in this case what I am having, I am seeing that I am left side of this dotted line, but this exponential dotted line. So my Cbj is forward biased, and I am below this horizontal dashed line. That means my Ebj is reverse bias. So this is the mode that is reverse active. Fine. So this is in the output characteristics of the plot. So now here I can see this is an NPN transistor. So this PN junction, emitter base junction, is at 1 volt greater than 0.7. So this is my significantly forward biased. So Ebj is forward biased, and my Cbj, this is N and P, N side is higher than P side. So this is at my reverse biased. So I am at the forward active mode. Is that clear?
Yes, sir.
Okay. I think it is already past 9, so we can stop here. From the next time we can discuss this. So I'm just putting this question so that you can ponder upon this. Okay, just I'm reading this question so that you can think, and while we can start next week, you can give me the answer directly. So the question is, NPN transistor, or for that matter PNP transistor, are basically two PN junctions back to back, right? So this NPN transistor we can get amplification. But in the lab, when you connect two PN junction diode, individual components, exactly same fashion back to back, you will not get any amplification. No amplification. So I need to, I want you to think about this, that why this equivalent circuit cannot provide you the amplification. Okay. So that in the next class when we start, we can directly start discussion upon that. The answer lies in this and in this diagram. Okay, whatever we have discussed today, you see the differences between two architectures, and then you come up with some answer. Okay, I think, yeah, I think we can close today. If you do not have any question, I would like to call it a day.
Sir, I want to know how we achieve the different types of concentration of doping within collector technology wise. Well, I
Oh,
mean,
okay. Technology wise, okay. So that is a very good question actually. So you see the we draw it like this, right? We draw the transistor like this, but it is never like this. So what happens? You have a base silicon, okay? Let's say you have a base silicon. Fine. Let's call it N type. You start with some N type. Fine.
yes, sir.
So you create a mask through which you apply your diffusion, and you make a portion of the thing p type. Okay, and then a process called photolithography. You are aware of photolithography?
Yes, sir.
So what you do, you create some boxes and you select some particular region where you put some light and do the etching, chemical etching, and then get back something something out. Okay, this is
Yes.
how you can do the selective kind of your selective kind of doping.
Yeah.
So that can be done in a vertical fashion. Is that all right? Or should
Yes,
I
sir.
explain more in this
No, no,
case?
sir. Yes, sir.
Okay. So if that is fine, so then what you do? You have your this p-type kind of oil, and then again you make some n-type, you make again some n-type oil. So this is your n-type, this is your sorry so this is your p-type. Let's say your base material was n-type. I am just showing you some portion, not all. So this is your, you do it n-type, n plus type, and then again you dope this portion p-type. Fine. So now what do you have? You put a contact here, so this become your emitter. You put a contact here, this becomes your base. You put a contact here, this becomes your collector. So this is how the actual BJT structure look like. BJT is a vertical device, okay? But to analyze, what we do? We just focus on this red part and then we flip it over. Okay, if I bring out this red part, what do I have? I have p plus plus n plus then p, and I assume that my contact is here. What is the difference between this? You will have a base resistance, this we call RBB. If you do the small signal modeling of BJT, you can see that this base resistance is a menace to get rid of. Okay, and then what we do, we assume that the collector contact is the bottom, because a collector contact will also have see some resistance, and then we flip this guy over and we start to analyze this part, p plus plus n plus p, and this is the PNP transistor that we read in the textbook, but the actual structure is this vertical structure. Okay, and this is something called, this is because these contacts are on the same plane, this is called your planar process. It can be done with Mesa process as well. This is another technique, old technique, but nowadays it all is done on the planar process. Does that answer your question?
Yes, sir, but I still don't get how different doping concentration is achieved in the same collector.
Acha, in the same collector you mean to say?
Yeah. Because you are doing the different types of doping, no? In the collector region.
Okay.
In some part we are doing
So
10 to the
your
power 8.
question is how this is done,
Yeah,
right?
right.
So see, this is also silicon. This is also silicon, right? Let's take a silicon slab. Let's dope it with 10 raised to 20, right?
Yeah.
Then I can all, okay, now I see your question. So it will be the opposite way around. So this is, let's say your 10 base wafer always starts with 10 raised to 17 or something, and then you try to dope this one 10 raised to 20, let's say, but then you need to flip the wafer over, then your polishing will be difficult. Okay. Okay, so currently I do not have the answer of this question. I'll come, I'll look into it and get back to you next week. Okay, is
Okay,
that
sir.
fine?
Oh, no problem, sir.
Okay,
Thank you.
but that is a very good question. Thank you. Something for me to learn as well. Thank you all.
Thank you, sir.